Hello, welcome to this video. In the last video, we saw how variables share same memory addresses and different memory addresses based on how the variables are assigned and referenced. We stopped at why they share the same addresses, that is same memory addresses, when the variable myNewNumber was assigned with the variable myNumber. Here, the variable myNumber has a value of 2019. MyNewNumber and myNumber share the same memory addresses. Why is the question we had in the previous video. We shall address this question with a solution in this video, but we also add a different question in our previous lecture. When we assign the value of 2020, that is a new value, to the variable myNewNumber got a new memory location, that is new memory address inside of the memory heap. That is, it got a new memory location inside of the memory heap and now has a different memory address. Before, myNewNumber and myNumber both had the same memory addresses. That is, myNewNumber shared the same memory address, that of myNumber. But as soon as myNewNumber got a different value, myNewNumber is no longer sharing the same memory address of myNumber. It got separated. myNewNumber became independent. Now it has a new memory address of its own. These two questions will be answered in this video. Before answering the second question, we shall see why myNewNumber and myNumber shared the same memory addresses. Let me go to the slide. Okay, in this slide we have 2019 value assigned to the variable myNumber, and myNumber has a place inside of the memory with an address of 54 54 54 5. myNumber has a value of 2019. When we create a new variable and when we assign it the value of myNumber, that is, when we assign the variable myNumber to the new variable, that is myNewNumber, JavaScript doesn't give myNewNumber a new place inside of the memory heap. What it does is it's assigning the same memory address, that of myNumber, to the variable myNewNumber. Here myNumber as an address of 54 54 54 5. myNewNumber is also going to have the same address, that of myNumber. JavaScript is doing this by assigning the address of the variable myNumber, and instead of allocating myNewNumber a new address, it tells myNewNumber that 2019 is already stored in the memory, and I am not going to waste my space by giving you a new place inside of the memory. You'll have to share a reference with 2019 which is assigned to the variable myNumber. Do or die, that's all you get. I am not going to give you a place inside of the memory heap. You might think, why is JavaScript Memory Manager being so mean? It does to increase performance and uses that space by allocating it to a different variable by freeing the memory in your operating system. Instead of allocating myNewNumber with a new place inside of the memory heap, it's going to give the space to a different variable which was declared or assigned with a new value. You get the idea. That's the reason why myNewNumber and myNumber are referencing to the same memory address. 2019 is all myNewNumber wants. What JavaScript is saying is that 2019 is already being referred by the variable myNumber. So why not use it? Because all you want is 2019, you get 2019. I am not going to give 2019 with a new memory address for you. Now, coming to the second question, as soon as myNewNumber was assigned with a new value, JavaScript Memory Manager, instead of referencing myNewNumber with the same memory address that it had before, it gave it a new memory address. JavaScript Memory Manager got disappointed and it gave it a new memory address. But why was it given a new memory address is a real question. It's not just with myNewNumber. If we declare a new value to the variable myNewNumber, let's say we are assigning it the value of 2020, that is, myNumber is getting reassigned with the value of 2019 plus 1, or myNumber plus 1, that is the value 2020. We might think that we are reassigning the variable myNumber by adding it 1 to it. The value 2019 now is getting reassigned with 2020, and so the memory gets a new value and is replaced with 2020. here my number as an address of 545454 with the value of 2019. We might think that the variable my number is going to have the same memory address, but the value of 2019 is going to get replaced with 2020. But that's not happening. My number is going to get a new memory address. Here in our example, we chose the memory address to be 242424, and the variable my number has the value of 2020 with a new memory address. This is happening because in JavaScript primitive values are immutable and number is a primitive value and it is immutable. That is the sole reason why my new number gets a new address, and also when the variable is reassigned it gets a new address. But with mutable objects that is different. That is arrays and objects, those are mutable objects. Here we have a variable of my array with the value of 1, 2, 3, and when we push the value of 4 into the array, that is my array, we get a new value, that is 1, 2, 3, 4. But the memory address is going to be the same, only the internal state of the memory address is going to change. Before, the value of my array was 1, 2, 3, and it had a memory address of 0x282828 with the value of 1, 2, 3. But as soon as we pushed the value of 4, we didn't get a new memory address. It had the same memory address of 0x282828, but the internal state of the memory address, that is the internal state of the value inside of the memory address, changed to 1, 2, 3, 4. Knowing when to use references can be a huge performance optimizer, because instead of creating a new memory address for each push value, that is, instead of getting a new memory address inside of the memory heap, we are having the same memory address but with different values. This can be a performance optimizer when we use the mutable objects wisely. In the last video, I briefly touched on the topic 3 stages of memory life cycle. We allocated variables inside of the memory, which was one stage of memory life cycle, that is, allocate the memory you need. And when you use the allocated memory, like sharing the references for example, is the second stage of memory life cycle, that is, use the allocated memory. And now we are slowly moving toward the third stage, that is, release the allocated memory when it is not needed anymore. To understand the third stage, we'll speak about the naive reference counting garbage collection. But before we go and start talking about garbage collection, let us take a while and talk a bit about reference counting. What is reference counting? Reference counting allows you to keep track of your reference objects created by your code on the memory heap, and allows you to keep track of how many references are still active. When the reference count goes to 0, you can safely free the memory used by the object. It is a way to implement basic garbage collection. But as said, we shall talk about garbage collection in great detail when we are done understanding reference counting. Let us have a look at an illustration. Okay, here we are assigning an array to a variable a which has a length of 3 with values a, b and c. Variable a as a reference to a memory address of 0x16102cf48. So the count of reference counter goes to 1 because the variable a is being referenced to the memory of 0x106. So this memory has one reference, that is a, so the reference count goes to 1. Now when we assign the variable b, when we assign the value of a to the variable b also has the same reference to the memory address of 0x106. So the memory address of 0x106 now has a reference of 2 variables, so the reference count goes to 2. For the last time, let's assign the variable c with the value of a. The variable c is now going to have the same memory address, that is 0x106. So the memory address 0x106 now has 3 memory references. So the reference count goes to 3. Now if we assign null to variable c, the reference count goes to 2 because c is no longer being referenced to the variable 0x106. So this memory now has only 2 references, that is a and b, so the reference count goes to 2. Similarly, if we assign the variable b with the value of null, the reference count goes to 0. Memory address of 0x106 now only has a reference to A. B and C are null, so the reference count goes to 1. Now if we assign null to the variable A, reference count goes to 0. But the variable A now has a different address. Null as a different address, null as the own address of its null as a different address, that is it has its own address inside of the memory. We shall see this scenario in the coding section, but as of now let's keep it simple. Null simply means nothing is assigned to that variable, and the memory address can be pointed to any of the thousands or millions of objects that's in the memory heap, just because the variable A isn't destroyed. This is reference counting. Now let us have a look at the naive reference counting garbage collection. And garbage collection is the third stage of the memory life cycle. What is garbage collection? Garbage collection is the process of making space in a computer's memory by removing data that is no longer required to use. In this example, when we removed the reference of A, B and C, these are no longer required for us. So the garbage collection is going to see the reference count, and if the reference count is 0, it's going to destroy all these variables A, B, C inside of the memory heap. Garbage collection is the process of making space in a computer's memory by removing data that is no longer required to use. As soon as the reference count goes to 0, JavaScript Memory Manager destroys that object, making space in the memory. But this is a naive reference counting algorithm and it has a problem. We shall go through the problem after the coding lecture, which is coming up next. The next video can be skipped, but I highly recommend you to go through the next video because we are going to see a special case where the value of A is assigned with the value of null, and null can be pointing to many different objects inside of the memory, and that value can have many reference counts, and we'll see that in the next video, that is in the next coding video. But if you feel like I don't want to see what's happening behind the hoods of Python, how the reference counting works inside of Python, then you can skip the next lecture. But I recommend you to go through the next lecture because we are going to cover an important aspect. Okay, don't skip the next lecture. Thanks for watching this video. See you in the next video.